that. Uh, right. So now let's continue from here. No, it's just your chat as well here, so I can look into that. All right. So let's do question number 3. Can you remind me if I shared this worksheet with you guys over WhatsApp? Did I do that? I'm gonna check it very quickly. I did not. Okay. I shared a PDF of capacitance. I think it was, yeah, I did share. I shared it. I just checked. Yeah, yeah. All right. Okay. So, I mean, that means you did not probably go through it. But so I don't know if but still, is there any question from anything that we have done so far? So I expect like when we do some of the questions from a worksheet, and after that the class is over, after you take a break, whatever, and sometime later, go try doing the questions yourself as well, right? And when you do that, that's when the problems, the doubts, or these things will pop up, and you can always ask in the next coming class, right? So if there is no question from so far, whatever we have done, we'll start with this question number 3. And the first 2 parts are very basic. State what is meant by electric potential at a point. This has to do with the work done in moving an electrical charge, right? So the electric potential at a point is defined as the work done in moving a unit charge from infinity to a point, right? So these are very basic definitions to that point, right? So that point, that point, as in this point that they were mentioning in the problem statement, right? Next, define capacitance. Capacitance is simply defined by the charge stored uh, per unit potential difference, right? The charge stored between the plates per unit potential difference between the plates. So you can define it as the ratio of charge stored to the potential difference. Right, and this is the same. This is this equation that C is equal to Q by V. Right. So I not expect that there will be any questions from this. Let's start this next part. That is the variation of potential V of an isolated metal sphere with charge Q on its surface is shown. So there is potential V in charge Q on the sphere. It's a spherical geometry, and this is how the potential versus the charge that is stored on this looks like. So we see that when the potential increases, it is capable of storing more and more and more charge. And if you go to the next page, we say that this metal sphere has some capacitance. All right. Use the figure 4.1 to determine the capacitance of this sphere, right? So we want to figure out what would be its capacitance. Capacitance is defined as charge divided by voltage, right? This looks like it can also be written as the change in charge by change in voltage. The units are the same, and it's, if I look at this thing, if I find the gradient of this line or pick any 2 points, I can just actually I can just pick 1 point, any 1 point on this line, right? And if I pick, for example, any so just give me a second, Q, right? So this is so let's pick this point, 1.1 for charge. I'm trying to pick a point that's lying exactly on the line. So we can take this one. I hope it's you can see this point. It is crossing this dot, and the value for charge is this thing, which would be, I think, zero. If this is 0.5, this would be 0.8, 0.9, 6, 7, 8, 9, right? So this would be 0.9, but remember it's in microcoulombs, so this is microcoulombs, and corresponding to this, the potential is 50 kilovolts, right? So it's 50 kilovolts. Right. So these are the 2 points. Now we have a value for charge and we have a value for voltage. Capacitance is C is equal to Q by V. So you just put in these values and figure out the solution, right? So this would be 0.9 microcoulombs. So that's into 10 raised to power minus 6 coulombs divided by the potential difference, which was 50 into 10 raised to power 3 volts, right? Because there was a kilo volts with it, right? And so this should give you approximately a capacitance of 1.8 into 10 raised to power minus 11, right? Farads. So they're asking the capacitance in farads, so I can just write down this value in this place. So 1.8 into 10 raised to power minus 11. Any questions from so far from this? Any questions? No questions. All right. Okay. So the next part, we have the electric potential energy stored on the sphere when charged to a potential of 150 kilowatts. So remember again, if I'm charging it, it's basically not storing that charge, but it's storing energy. And we want to find out this potential energy that is stored in the sphere or on the sphere actually when it's charged to a potential of 150 kilovolts. So that's, again, it's pretty straightforward. If you remember that this energy stored is just the work done, right, which was half CV squared, right? And now you could have used this, and we know the capacitance as well, so we can use this capacitance. We could have also went along and used this thing that energy is half Q Q times V, right? Half Q times V, because capacitance is Q by V. So this would mean the same thing. And I would just have to look at this value for potential. They're saying to 150 kilovolts. So for 150, I'll have 150 kilovolts in voltage and a corresponding charge from this thing. So I'll see that this is 150 and I'll see where this cuts this line, and whatever charge do I get from here would be the value for charge. That's one way of doing it. The other way is very simple one where we have already figured out the capacitance. So just use this part of the expression, half CV squared. That's half into 1.8 into 10 raised to power minus 11 farads times volts squared. Volts is 150 kilovolts, right? That's where we have to see what energy is stored. So 150 to 10 raised to power 3 volts. And so we see the units are volts, farads, or we have all SI units. This would give me joules and 0.20 joules, right? So 0.20 joules. Okay, so that's how you find the energy. C part says that a spark reduces the potential of the sphere from 150 kilovolts to 75 kilovolts. So what happens is you have this sphere, you're storing charge, but eventually what happens is a spark happens. When a spark happens, you know that the two opposite charges combine, so that that energy is lost into combining these two charges. And so then now those charges are gone. So that part of energy is basically gone from the capacitance, and it should lose it should lose some energy. We want to figure out that loss in energy, and that loss in energy can be figured out by simply using this thing, that work done is half CV squared, right? But the thing is that, again, this is loss in energy. So we'll say delta E is equal to half C times VF squared minus VI squared, right? And then you just put in the values. Half into the capacitance is 1.8 into 10 raised to power minus 11 farads, and the voltages are, so the final voltage is reduced. So this would be 75 into 10 raised to power 3 volts squared minus 150 into 10 raised to power 3 volts squared, and this thing. So this, they're saying, again, remember, they're saying compute the energy lost from the sphere. So this would give you a negative answer, but you would write it as a positive because this is the energy lost. This negative sign is showing energy lost, and you'll just write that the energy lost is 0.15 joules. Does that make sense? All right. Quickly. All right. Okay. So next we have this question number 4, and here a capacitor consists of two metal plates separated by an insulator, as shown in this figure. We see that we have this is a capacitor. Both are metal plates, and insulator is sitting inside these plates. So it could be air or any other insulating material. The potential difference between the plates is V. The variation with V is shown according to the charge. So here we have charge. Note that this is in millicoulombs. So that's into 10 raised to power minus 3. And here we have volts, which does not have any prefix next to it. All right. So now they're saying the first part, they're saying explain why capacitor stores this thing stores energy, but it does not store charge, right? So as we saw in our lecture on capacitance, that when we have these plates of the capacitors, so one of them has positive charge, the other one is negatively charged, and they're connected to a battery, positive, negative. And what happens is that the charges are on these plates are really equal and opposite, which means that if I were to add these charges, the net sum would vanish or give me 0. And that means that there is no net charge stored on the capacitor. And so we cannot talk in terms of, we cannot say that there is any charge stored on the plates of the capacitor. But because of the fact that the two plates must be separated, there has to be some work being done that keeps or separates, that this work is separating the two plates from each other. And that's where the energy is stored. That work is the energy stored in the plates of the capacitor because of the conservation of energy, right? So you can go ahead and say something like that. The charges stored on the plates of the capacitor are equal and opposite. Right? So what would that mean? That means net charge vanishes or is zero. So so with this, you are basically implying or defining or telling that why charges are not stored on the plates of the capacitor. But now you have to argue why is energy stored, right? So the energy is stored as the work done to separate the plates. Right, because they're positive and negative plates, so they should be eventually coming into contact with each other, but they're not. And the work that is being done so that they do not touch each other is the charge that is stored between the plates of sorry, that is the energy which is stored between the plates of the capacitor, right? Okay, so let's move on to the next part. Using figure 3.2 to determine the capacitance of the capacitor, a very similar problem to the one that we have just finished. If I have this graph, now note that on this thing, I have on vertical axis my charge, but on the horizontal, I have voltage, right? So I can simply find out the gradient of this line, which would be, so the gradient of this line would be change Q2 minus Q1 divided by V2 minus V1. This is just delta Q by delta V, which is basically just the capacitance, right? So that's one way, or again, you could just pick one specific point on this line and figure out the value for the capacitance, right? So for example, you could pick this point. Let's pick this one. So if you again see the coordinates for this point, I'm not going to repeat that again and again. So the coordinates of this point would be on the x-axis, which is the voltage. It's about 10 volts, and the charge at that particular point is about one or we can say 18 into 10 raised to power minus 3 coulombs, right? Minus 10 raised to power minus 3 because there is a milli in this thing. So this gives you the values for voltage and charge. Now it's just a matter of using this equation that capacitance is charge divided by voltage. So this would be, as we saw, the charge is 18 into 10 raised to power minus 3 coulombs divided by 10 volts. And this would give you 1800 into 10 raised to power minus 6 farads. And because they are saying give the answer in microfarads, I'll just write this 10 raised to power minus 6. I can replace this with the unit micro, the prefix micro, and this becomes 1800 microfarads. Right? So that's the answer. Is that clear? Any questions from anyone so far? All right. So again, it's a similar question. I was expecting that. Let's see. Yeah. Okay. So, anyways, the loss in energy stored in the capacitor when the potential difference is reduced from 10 volts to 7.5 volts. Again, it's exactly the same thing. You can do. There are two things that you can do to work this problem out. One is just simply use this expression that this loss in energy stored is basically the work done, which is half CV squared, right? And then use the same procedure as we did previously. The other thing that we can do is, as we saw in the lecture on capacitance, that the energy stored is really the area under this graph, the charge versus voltage graph. So they're saying that from 10 volts to 7.5 volts, which means that the maximum voltage would be 10 and the minimum voltage should be 7.5. And from there, you could make a triangle, right? So let me see where would be 7.5. So if this is 5, 6, so how many boxes are 5? Okay, so the graph doesn't look really clear to me. Let me see. But yeah, so 7.5, maybe it could be somewhere here. Let me see. Yeah, somewhere over here, right? And so the maximum is this. So you'll just draw something like this. This would be a triangle, and you can easily compute the area under this part of the line and find the energy stored. The other method is the same one that we have been using so far. As we know, the capacitance, this would be 1/2 into 1800 into 10 raised to power minus 6 farads times the final voltage, that is 7.5 volts. So 7.5 volts squared minus the initial voltage, which is 10 volts squared, right? And if you do the math, this gives you about 39 or 40, 39 into 10 raised to power minus 3 joules, right? And so that's the energy that is lost in reducing the potential difference. And there, so you have to make sure that the units are matching. This unit has a prefix milli with it, but we know so 10 raised to power minus 3 is just milli. So this would be 39 millijoules. All right. So the next part, which is part C. Okay, so here we have 3 capacitors, X, Y, and Z, right? And all of them have a same capacitance of 10 microfarads. So let's just write that down over here, 10 microfarads, 10 microfarads, and 10 microfarads. These are connected in this way. So you see that there are 2 capacitors connected in parallel and then one in series to that parallel combination. And initially the capacitors are uncharged. Now a potential difference of 12 volts is applied between points A and B. So you could do that by attaching a battery to these points A and B. This could be done. This would be one way to apply this potential difference with an EMF of 12 volts. And determine the magnitude of the charge on one plate of the capacitor X. So we want to figure out what charge would be stored on the plate of the capacitor X, right? So how do we do that? First of all, if I can figure out the, let's start solving this circuit first of all, right? So I'll have to figure out the total capacitance that comes from Z and Y. So that would be an equivalent of a circuit that would look like this, where this new capacitor, which is this one, is just a combination of the sum of these two, the parallel sum of these two. And what would that be? If I do the parallel sum, that would be 1/10 microfarads plus 1/10 microfarads, and then take the inverse of this. And this would give me the combined capacitance of Y and Z together as 20 microfarads. Right. So that's this capacitance of 20 microfarads. And then you have here 10 microfarads. Now, because these capacitors, all of them are 10 microfarads each,
This means that the potential difference across each capacitor can be determined quite easily, because across the combination, the parallel combination of the capacitors, the potential difference would always be the same, right? It would be, if I measure it across this capacitor, it should be the same as the one that is coming from the battery. That's 12 volts, and this should be also 12 volts. But in series, it is divided into the algebraic sum, which means that we would be left with so 2 over here. So we would be left with 8 volts over here. Now, if I have the potential difference across these capacitance, right? So this is the capacitor and the potential difference as well. Then I can easily figure out the charge, right? And I want to figure out the charge across X. So I can just use these values for X, because I know that charge, the capacitance was defined as charge divided by voltage. So charge is just C times V. And the capacitance for X capacitor is 10 microfarads. And the voltage is 8. So you can write this as 10 into 10 raised to power minus 6 farads times 8 watts. And this would give you around 80 into 10 raised to power minus 6. I mean, obviously, it would give you this thing, right? So this would be 80 microfarads. Sorry, should be 80 microcoulombs, right? Because this is the charge. Right, so that's how we'll figure out the charge, and they're asking it in microcoulombs as well. So this would be 80 microcoulombs. Any question from this problem? Sir, aren't you doing the opposite way? And no, I mean,